We are the Unity simulator for robotics group. Our team consists of 7 members, which is divided into 2 subgroups, which is the Unity side and then the web side. We'd like to thank our sponsor, Professor Chen, for taking us under his wing and showing us this and helping us and mentoring us through everything.
Our project is basically developing a robot using Unity 3D, which will be able to be controlled using Bible commands.
And those commands will be sent through a protocol, which when those commands are sent, the robot should be able to act upon those, such as move, navigate through a maze, and turn and rotate. Another of our objective is to establish a connection between Unity and the web page, and another connection between Unity and the web page, which will display coordinates, movements, and the maze. There was a few problems we'd run into, so we'd have to do some basic researches in those areas, which is establishing a connection between Babel and Unity, building a database to store the data from Unity, transferring data from Unity to a web page, displaying data such as coordinates, maze, and the time in an HTML canvas. In order to complete all this, we'll have to find solutions and implement them to get a perfect running robot.
Because this project has 2 distinct parts, a Unity side and a web side, we divided our team into 2 sub-teams with a Unity team and a web team. The Unity team consists of Kai Wang, Yufeng Ouyang, Minghao Wei, and Zhechen Wang, and the web team consists of me, Chris Sims, and Kent Morrissey. We also have one specialized role responsible for integrating the 2 sides, and the person responsible for that is Mustafa Salih. On the web team side, there are really 3 parts. There's a web application, a backend database, and an API. The web application is basically a graphical representation of a robot moving around on a map, and this will have to be animated based on data received from the backend database. The backend database itself is basically a storage for simulator information received from Unity, and that information is received via an API, which facilitates a communication between the Unity simulator and the web server.
So the project contains 2 components, one of which is the front-end web application, and that's going to be a multi-component application. The first thing that we're looking at, we want to have a graphical representation of the robot activity, meaning we're going to have sort of a line tracing where the robot's going on the screen. Not a very complicated animation, but just a sense of, so that someone watching can get a sense of the path. And then alongside that, we're going to display data related to the position and the movement of the robot. For instance, the direction of the robot, its orientation and its coordinates on an XY plane, and then later on down the line, probably later on down the line, an XYZ plane. And then lastly, we would have something like the velocity and whatever else we feel is most important to aiding the project. So this is all sort of in flux. And then the way we're going to do that is we need to be integrated with the back end. We need to pull the coordinates and the information sent from Unity to the database onto the front end so that we can understand what to parse and what to calculate and what to display.
So I'm responsible for the actual maintenance of the server itself running our application on the website, the backend database on the server, and also the API that we're going to use for the Unity server to communicate with the web server. The server itself is an Ubuntu Xenial server running 16.04 LTS on a VPS, and managing that server entails a few things. Configuring accounts for all of our users, accounts for databases, and the management of those accounts, which includes distributing their credentials and telling everybody how to use them. Configuring the firewall on the server and keeping the server up to date and making sure it's secure. In terms of the database itself, the database we're using is called CouchDB. It is a NoSQL document store. It's very lightweight and perfect for our project because it's very easy to implement. It's lightweight in that it's a NoSQL document store. It has a built-in JSON API, which is huge for us. And that API integrates perfectly with HTTP requests. Basically how this works is you can read and write from the database using HTTP requests out of the box, and you can turn that on so those operations can be done remotely. So that means that we spend less time building our API and using the tools available in the database itself, which allows us to focus our energies on other things like web application design and integration. So the API is basically used in a few ways. To write to the database, you use HTTP put. To modify the database, you use HTTP post. And to get documents from the database, you use HTTP get.
One part in all of this is to integrate a connection between the Unity simulator and the web server, which will be able to send data from Unity to the web server. This should extract data from the Unity simulator, package it all into a defined format, which is a database that Chris has created, and send that data to a web server via API. The web server needs to be able to receive data from the client running the simulator. Mostly accomplished by the backend development, and it's also important to define the data format that will work with both sides of the servers.
So here's the methodology that our Unity team is going to use. So basically, first of all, we need a human robotic object, and then we're going to find our algorithms for the maze solving, and then also for the last part is use WIPO to support our controls. For the humanoid robotic, it's supposed to move smoothly as a real humans, and then for the algorithm, there are multiple algorithms out there. We got to find the one that actually can solve the maze effectively, and then for WIPO, it actually supports multiple platform of robot, so it should actually support different kind of robot. What is a Unity? Unity is used to develop video games for PC, consoles, and mobile devices and websites. It is a multiple platform game engine, as you can see, actually supports as this many platforms and then much more. Maybe just didn't mention. It's a very powerful tool for game developers. Why use Unity? The current version of the simulator is only a 2D web simulator, which is written in HTML5 and JavaScript, which just needs to be imported. We want a 3D version of the simulator to be running, and the robotic and the robot in this current simulator are only allowed to turn in 0 or 90 degrees, which is not realistic at all. And the Unity will give us a more accuracy and animation. So this is what we try to achieve for the robotic object. We want a humanoid robot similar to this, but not exactly like that. So the current robot we have is a cube, which cannot be called as a robot at all. That's why we want to replace as a human robot to make it more realistic. This is what you can do in Unity. You're actually able to kind of like create multiple 3D objects. We use them to form our robot. All those objects can be formed in a group. They can kind of like become one individual object, or they can be combined together to move together, and then it also allows the cameras, direct light, all kind of stuff to kind of support our built-in function to make our robot simulation looks better and then looks stronger. So this is how we're going to write code for the Unity. It actually supports C# and JavaScript for scripting, and we're going to use C# in our projects. There are multiple scripts that we are majorly focusing on. One is for the object movement, how to move the object. We should have the object move by remote control or automatic, and also the sensor reading. There's multiple sensors supported by the Unity: color sensor, distance sensor, and then sensor else. We need to write a script to actually getting data from those sensors and then processing it. For the data processing part, we are able to kind of like combine the data that we have in our simulator to actually write in either JSON or HTML file, in this case, to processing our data.
Our target is to make our robot be able to travel through a maze. So I will introduce some of the basic algorithms we're going to use for maze solving. So one of the most straightforward one is called wall follower, and it's also known as right hand or left hand rule. And basically, I put a picture here to show that. So basically, what we do is to keep the robot's one hand in contact with the maze wall. So here, this is a right hand rule. So we keep the robot's right hand in contact with the wall. So the robot keep following the maze. And so by doing this, the robot is guaranteed to never to get lost in the maze. And it's guaranteed to find the exit or entrance. So one way to understand this is that because this wall is connected, so you can deform this wall into a circle. And so this algorithm works like that. The robot goes through the circle from the start to the finish. But this algorithm has some of the backhands, which is I saw in the next slide. Okay, so here's one of the scenario that this algorithm will not work. So here the agent travels from the start, and this is the left-hand rule, and when it goes like this, it gets trapped here because it doesn't just keep it turning left, and it's never going to find an exit. And one way to solve this problem is to use the patch algorithm. This algorithm keeps track with two data. One of the data is the angle the agent is currently heading, which is called heading here, and the other one is the sum of the turns, which is total of the angles the agent has traversed. So here is that, for example, when at the entrance, the angle of the heading is 0, and the sum of the turns is 0. So the pledge algorithm keeps that the agent will only leave the wall when the sum of turns and the headings are both 0. So you see here, at this angle, the heading is 90, and the sum is 90, and it keeps going like this, and okay, when it's here, because the sum of the angles it traversed is not 0, so it's not going to leave the wall. So it's not going to like turn left as shown here. It's going to keep in touch with the wall and turn right, and it goes like here. When the sum of the angles and the headings are both 0, it leaves the wall and leave the maze.
Hi, I'm going to introduce WIPO. So what is WIPO? WIPO is a virtual programming language environment. In other words, this is like a programming language like C or Java. It can use to control a robotic in an easy way. So because it is easy to use, it is designed to the program beginners and the students who don't have programming background. And it has open APIs and interactions, so it can support a variety of robotics. Here is a wiper example. This is a program to control a robot by keyboard. Here is this function block is used to create a robot, and this function block is to capture the command from keyboard and send this command into this function block. So when you press W, the robot can go forward. And here is another example of wiper. It's much more complex, but it created an autonomous robot which can find a way to go out the maze autonomously. We can see that this robot will never hit the obstacles. When it's going to hit the obstacles, it changes the direction. Like this, it changes direction. So what are we going to do with wiper? At present, wiper provided limited functions. Like this. This is designed for a robot like a car. So if we design a human-like robot, we cannot use these functions. So therefore, we need to create more functions on wiper to control a human-like robotics.
Here we have the timeline of the project. The first slide being what we've done so far. At first we implemented a simple animation in the web application, which is actually divorced from what we're going forward in the project, considering we're just going to have a line trace. But in the meantime, the Unity side of things has animated a simple robot in Unity, and then we've designed the web stack, we've designed the web application as I detailed before, what components we're going to have, and then Mustafa has implemented the means to extract data from the Unity simulator, which is obviously crucial to communication, and then we've determined the structure of the kind of data that we want from the Unity simulator, and then lastly, for what we've done so far, we've defined the data structure that maps to the Unity simulator data that we want to send to the web server from the Unity simulation. And then we have tasks in the near future. What we're doing this week is we're going to have Chris install the web stack on the web server. We need to implement a means to receive data from VIPO, the visual programming language that drives the Unity simulator. We need to make sure that communication is correct. And then we need to, for instance, implement the mapping of the raw Unity data into our defined data structure. And then we need to determine the document structure for CouchDB, the database technology we're going to use. So, we need to make sure that everything maps to each other so that it's a very streamlined communication process. And then we have the final tasks for this semester. Once we have the basic communication working, then we need to decide, okay, we have the data, what do we do with that data? We need to, for instance, identify statistical models to be used in the analysis so that we know what we're going to be presenting on the web simulator in terms of statistics and data representation. And then on the Unity side, we want to animate a realistic robot in the Unity simulator rather than a simple rectangular prism just moving around a maze. And then obviously, we need to make sure that there's communication that's possible, so we need the interface on the web server for receiving data from the system from the Unity simulator. And then we need to write the JavaScript or whatever programs we're going to have calculating running the statistics and calculating what we wanted to display, and we need to write that script. And lastly, the final goal for the end of this semester is to write some programs that allow for the robot on the Unity side of the simulator to solve a maze using the right-hand rule following algorithm. And then we have tasks for the beginning of the next semester. So on the Unity side, we expect to have the right-hand rule solved. So then we need to we want to have the website of that enabled. We want the browser to display the path of the robots and the coordinates and so on and so forth, so that if the robot solves a maze, the website can show that. And then if we have multiple robots working, we need to assign a unique identifier to each robot so that the website is able to distinguish what coordinates goes to which robot goes to which line. And then what we want to also do on the Unity side is have the robots be able to have a representation of the maze beforehand and be able to calculate an algorithm without using something as simple as right-hand rule following, create an actual graphical traversal of that. And then, we want to obviously improve the coordination and the number of joints on the robot. Then we want to explore the process for sending dynamic edge links, so traffic to the maps in the Unity simulator, so that the robots can experience what happens when maybe one path that used to be the best path turns out not to be such a great path. And then, for example, we also want to write the code for the robots to assess the shortest paths and traverse them according to dynamic edge lengths as described previously. And then on the website, for example, we want to continue to look at historical data and analyze what can be done to improve robots' performances. So if you want to look at a particular algorithm and a robot and a traversal, you can see, okay, well, here's how it's done over time under these conditions. And then we just want to keep improving and streamlining. And then we want to add new features to the website, for instance, to account for the z coordinates. If the robot changes height in the Unity simulator, we want to be able to display that on the website. And then obviously we need to extract that data from Unity, and then we just want to consider on the Unity side how to improve robots' performance given all the historical data we've taken. Okay, so we know what works, what doesn't. How can we continue to improve? And then we just want to keep making things more difficult by introducing more traffic, and just every time we get better, make it a little bit harder and see if we can keep improving the robot's performance. And then finally, we are going to want to, on the website, change the web script to display the orientation of a robot during path tracing, so that if it rotates, the web can display that. And then we want to make sure, as the process grows, maybe the data structure is changing, we want to make sure that we have an adaptive design that doesn't get bogged down in what we used to be doing. And then on the website, if we have time, we want to design more complicated representations of humans or other things at the discretion of Professor Chen. That would be on the Unity and or the website. And then at the end, we want to begin preparing final documents and reports and submissions. And the timeline we've given is fairly ambitious, so if we have some things that we didn't get done by this point, by March 31st, then catch up. So that would be the timeline that we proposed, and we hope we can make good progress on that as we have so far.